Hi everyone, welcome to EE323, lecture 20. I'll be talking about op-amp based integrators today and some of the non-idealities associated with these integrators. I'll talk briefly about op-amp differentiators as well. You can find this in your book in section 2.5. All right, so first question that would naturally come up is why do we care about integrating a signal? And there's some sort of more obvious examples. For example, in a cell phone, there's a little MEMS device, a micro-electromechanical device called an accelerometer. This accelerometer measures acceleration. It's got this little tiny proof mass in there. And it turns out if you integrate acceleration, you would get velocity, and then if you integrate velocity, you get position. So you can record your position and velocity by integrating the signal. Now you could let a CPU handle this. But to reduce the load, if you're doing this frequently, you might have a dedicated hardware to do this, such as an integrator. Now, there are other examples. There are sensors that require integration of signals. There are computing techniques, analog computing techniques that use integrations. There are lots of examples of where dedicated integrators are used. So the standard integrator configuration is shown here. You can see it has an input VI on the left and output VO on the right. Now you might notice that this looks very similar to an inverting amplifier configuration, except now we have an R on the input to the negative terminal, but instead of an R2 on the right, this has been replaced by a capacitor C. So this is the inverting or Miller integrator. This is the standard configuration. So one example for this might be if you had a square wave input as shown below, and you integrate this, you end up with a triangle wave at the output. So let's dive into the details a little bit more closely of this Miller integrator. So first of all, if this were a resistor, we would recognize that the gain of this circuit would just be minus R2 over R1. So if we treat the capacitor as an impedance and the resistor as an impedance, we could write that the gain would be equal to minus Z2 over Z1. And in that case, we would say that the gain is equal to 1 over SC divided by R minus, and so the gain would be equal to minus 1 over SCR. So that tells us that V out of S over VI of S is equal to minus 1 over SCR. Now you might remember that 1 over S in the S domain corresponds to integration in the time domain. But let's prove this to ourselves a little bit more than just relying on a Laplace transform. So to do that, let's start analyzing this circuit. So the first thing we'll notice here is that the current, we remember that the current through a capacitor, we'll call it I1 in this case, this current I1, is equal to C times dVc dt. So if we separate this, we would get that I1 dt is equal to C dVc. Keep in mind where Vc is the voltage across the capacitor. And so we can integrate both sides here, and we'd write that 1 over C times the integral of I1 of t dt is equal to the integral, this should be dVc, integral of dVc. And so what we get from that is we get Vc of t minus Vc at time 0 is equal to 1 over C times the integral of I1 of t dt. If you perform that integration, the result, what you get on the right, on the left here, is the result. And it says that Vc of t is equal to Vc. Keep in mind this is the voltage across C at time equals 0. That's this voltage here, so that's the initial condition. And then we have an integral from 0 to time t of the current coming in, I1 of t dt. Just for your reference, this is equation 2.25 in the book. Okay, so we see that it integrates the input current. And so now if we rewrite the input current, and we say that if we substitute I1 as VI of t over R, right? VI of t over R is the current I1. Keep in mind that the voltage is 0 volts at the negative terminal due to the negative feedback. If we substitute that in for I1 into this equation, what we get is that Vout is now minus, Vout is minus Vc, right? It's the opposite polarity of Vc. And so that becomes minus 1 over RC integral VI of t dt minus Vc. And what we see right away, you can see that the R gets pulled out. And what we see right away is that the output voltage is proportional to the integral of the input voltage. So this tells us that indeed the signal is being integrated. Now what you can't see because it's behind the video here is Vc. This says initial condition. And RC is the time constant. Okay, so we understand now that this is integrating our input voltage. There's a initial condition and there's a time constant associated with this integral. Now if we looked at this, the frequency response of this, we remember that, keep in mind that V out of S over V in of S is equal to minus 1 over SCR. So the magnitude just goes as 1 over omega CR, going down at minus 20 dB per decade. And the phase, because it's minus 1 over J, the phase is plus 90 degrees. This is what's called the integrator frequency here, 1 over CR. All right, so that's basically how the integrator works. Now let's start talking about a little bit more about the non-idealities of this integrator. First thing is, what happens at DC? If we have a very low or DC voltage coming in, well, what happens to the output of our integrator? So keep in mind that the impedance, if we think of this as an impedance divider, right, and V out over V in is minus Z2 over Z1, where Z2 is coming from our capacitor C. As the frequency gets lower and lower, remember this is 1 over SC, as the frequency gets lower and lower and lower, that impedance gets bigger and bigger and bigger, and it tells us that our gain can basically explode, goes to infinity, right? So why? Basically, as that impedance gets larger and larger, there's no feedback, and you're basically using the open loop gain. You're using the op amp in an open loop gain configuration. So basically what this tells us is that if we have any DC input, right, coming into our circuit, that our output will saturate. This is clearly not an ideal situation for the output to saturate with a DC input. So the integrator saturates with the DC input, and so the obvious solution would be, well, let's just only use this then for AC signals. We won't apply a DC input to this. Fine, that's okay. But there's one DC input that you can't really avoid, and that's that DC input offset voltage that we talked about in the previous lecture. So what happens if there's a DC offset voltage? Remember, this offset voltage comes from fundamental mismatch, right, in our transistors. The offset voltage, the current from that offset voltage, remember that the negative terminal will now get that offset voltage, so that's VOS. So we're going to get a current flowing to the left that's equal to VOS over R. That same current will flow through the capacitor. And so what we'll get is that V out is VOS plus 1 over C times the integral of VOS over R. And since VOS is constant, or DC, we get that the output voltage here is just some initial condition VOS, and then it was VOS times T over RC. So basically, if we were to plot this now, right, what would happen is we'd start at VOS, this initial condition right here, and it would rise and rise and rise, and then eventually just saturate. So what this text here says is that the output will saturate even if the integrator has no input signal. So we're going to get a saturation with no input just from the DC offset, right, that is created by the mismatch in our circuit. So this is obviously clearly, by the way, this VOS over R here, this is just I of T, right? That's this current here, that's I. And so this is clearly not a great situation. We have, of course, we're going to have a DC offset because there's always going to be mismatch. Therefore, our integrator's always going to saturate even when we don't have an input coming in. And so, yeah, this is a major problem. We have a similar problem with offset with input currents. The input current will also saturate. And one trick we can try to do to help with the input currents is putting a second resistor R in here. So now we're looking at the effects of these bias or input currents in addition to the, in place of the offset voltage. And so what happens if we put a matching, notice that the resistor is the same value as our resistor, so they're matching resistors hopefully. And we're going to get a current coming in, IB2, and so this voltage will be minus IB2R right here. That gets mirrored to the negative terminal, so that's also minus IB2R. So we have the same voltage at the positive and negative terminals of minus IB2R. Now if we look at the current I1, right, we could say that that current is the voltage across the resistor, across that resistor divided by the resistance. The voltage is IB2R divided by R. So if those resistors are matched, these R and R, then the current I1 is also equal to IB2. Now if we solve for the current I2, that is the current that's flowing onto or off of the capacitor, that is giving us in other words, it's giving us an output voltage. We solve for I2 by KCL at this node right here. We can write that I2 is equal to IB1 minus I1. Remember, I1 is IB2. So what we see here is that I2 is equal to IB1 minus IB2. And if IB1 and IB2 are perfectly matched, then I2 is equal to 0 and we get no output, which is great. But if I2 and if IB1 and IB2 are not matched, that is, we have some input offset current, that is the difference between IB1 and IB2, then I2 takes on that value of this input offset current. And again, what happens is that the output voltage is now starting with IB2R at the negative terminal, and then we go IOS times T over C. So the same thing happens, that we're going to start at some voltage, this thing is going to go up and then saturate again from the offset current. So both situations with bias currents, input offset currents, and input offset voltages, they all create this saturation effect in the integrator. So obviously this is not a good situation, and so the solution here that's typically used is to add a resistor RF, now a feedback resistor, in parallel with C. And basically this provides a path, a DC path, so we don't constantly integrate charge onto that capacitor and create this saturation condition. The DC currents, we have this V offset over R, right? Because we have offset here. We have an I offset from the difference in the two base currents. Now they can flow through RF instead of through the capacitor. And this does generate an output voltage, but it's generally small. And so this is a much better solution than just leaving the capacitor on its own. And so what happens then is that we get an output DC, right, which would be the VOS. If we had VOS here, then it just looks like a non-inverting amplifier, 1 plus R2 over R1. IOS is just going to be flowing through here, so that will be flowing through there, IOS. And so we're going to see that the effect in a DC sense, we're going to get a DC voltage, keep in mind a DC voltage at our output, V out DC, with this particular value. And so the offset voltage and offset current create a constant voltage at the output, and critically it's not time dependent. That is, it's not saturating our output. Now if you wanted to minimize this output DC voltage, you want to choose a small value for RF. However, a small value for RF affects the transfer function, and I'll explain next how that works. So in the ideal case, without RF at all, you can see we have this problem with saturation. And then if we add an RF and we let RF get arbitrarily large, we're basically going back to that case where we only have the capacitor. So if we look at the transfer function of V out over Vs of this integrator, we see this RF over R over 1 plus S CRF. And if we let RF tend to infinity, this reduces to 1 over S CR. And so the ideal transfer function is this. So as RF gets bigger and bigger, it gets closer to this ideal transfer function. But it also increases the DC gain. So there's this trade-off between the DC gain and how close the integrator gets to the ideal integrator function. And so what this text says is trade-off. Higher RF is better if you don't mind a finite DC output due to VOS and IOS. So higher RF creates a higher DC output, right? But it gives you closer to this ideal transfer function. So if we look at the transfer function, the ideal case and the case with RF in there, what we see is this corner that's introduced at 1 over C RF. And as the frequency moves to the right as RF decreases. So as RF decreases, this moves to the right and creates a less ideal transfer function. As RF increases, it moves to the left and creates a closer to the ideal transfer function. So there's this balance between how big and how small you make RF. All right, and the last circuit we're talking about in this lecture today is a circuit called a differentiator. And as you might expect, this differentiates the signal rather than integrates the signal. So you can see in this case, the resistor and the capacitor are now switched. And so we could write that V out of S divided by V in of S is equal, again, use the impedance divider technique. So that's just R over minus R over 1 over SC. So that's equal to minus SCR. Keep in mind this corresponds, again, in the Laplace to time conversion to differentiation. Just to prove it to ourselves, more in the time domain, we have our input here. Our input Vi of t. We have 0 volts at the negative terminal, and so I of t coming in here is just C dV dt. And now if we solve for V out, because that's going through a resistor, what we get is that V out is equal to minus IR, so that's equal to minus RC d Vi of t dt. So indeed, this does differentiate our signal. So you can see this differentiation going on here. It differentiates the input signal. We look at the frequency response of this. What we see is that it's just going up at plus 20 dB per decade. Again, we have this term 1 over RC, which is the differentiator time constant, and the phase. Remember, this was V out over V in of S. This was minus SCR, so the phase is equal to minus 90 degrees. Now, it turns out the differentiator is not used all that often, nothing like the integrator. And one of the reasons is that it's not really that practical because it has some stability issues. And what I mean by that, in the ideal case, if we had a triangle wave and we could differentiate that and create the square wave. But if you add a little bit of noise, right, we're taking the derivative of that signal. So any little noise where the signal is changing rapidly results in a really large and distorted output because of the noise. So it's very sensitive to noise. It magnifies noise, which is sort of the opposite of what we normally want to do in our circuit. So differentiators are not used very much, but the integrators are used all the time. Thank you.